Got chapter 2 here, notes 2.1, rewriting absolute value functions as piecewise defined functions. Consider the absolute value function f of x equals 2 times the sum of the absolute value of x and 2. Then subtract 3. Sketch the graph on the set of axes below. Well, hopefully you recognize that the vertex for this little fella is the ordered pair -2, -3. And that is because subtracting 2 on the inside affects the graph horizontally. This is x minus a -2 technically. So we're going to go left 2. And then subtracting the 3 on the outside affects it vertically. We're going to go down 3. That's going to put our vertex right here. This is an absolute value function. It still opens up because the lead coefficient is positive. Since this coefficient is 2, it dilates the graph by 2. What does that mean in the context of an absolute value function? It means where the slope was originally 1 and -1, we now double those slopes, and we're going to get 2 and -2. So we're going to go up 2 and to the right 1 on the right side. We're going to go up 2 and to the left 1 on the left side. So we sketched it. We did that. Should box in the questions. We sketched the graph. Now, write the graphed function as a two-piece, piecewise defined function. So before we get into what the actual functions are, let's do the easiest part. We have this part of the graph here, and then we have the part that's to the left of that, which would be here. So our domain gets separated where that vertex is. So we have x is less than -2, and we have x is greater than -2, to the left and to the right of the vertex. Now the vertex needs included in one of these, and it doesn't matter which one you include it into, because you could include it into this one and it would be fine. You could put it in this one, it would also be fine. I'll just put it here at the beginning. If we don't include it in either, there's going to be a hole in the graph, and this clearly does not have a hole in the graph. The equation on the right is linear. Its slope is 2x. Pardon me, its slope is 2. So the first term is 2x. What is its y-intercept? Where it clearly shows here that it's 1. So this right side is 2x plus 1. So when x is greater than -2, f of x is 2x plus 1. This left side has a slope of -2, so it's -2x. What's its y-intercept going to be? Well, if we extend this down, I think we would see that it's going to be -7. There's some algebra you can do to figure that out. One way to look at it, using logic and not algebra, the vertex down here at -3. One of these graphs, the y-intercept is 4 above it, so this other one's going to be 4 below it. It's going to put you at -7. Algebraically, you could do some other stuff, but let's not overcomplicate this. So we finish that. Write this as a piecewise function. We did it. We have the constraints listed. That wasn't too difficult. However, some of these problems do get difficult. So we need an algebraic analytical strategy that we could write an absolute value function as a piecewise function without having graphed it. So that's what we're going to do here. There is 4 steps that we're going to follow to do this. And we're going to read the steps together, and then we will do what it says to do in an effort to try to see how to do this. Number 1, set each expression inside an absolute value equal to 0 and solve for x. So in this problem, we only have one expression inside an absolute value, and that's x plus 2. So it says take that expression, set it equal to 0, and solve it. We solve it, we get x equals -2. Easy enough. Step 2, draw a number line. That's just a fancy way of saying a line with numbers on it. And divide it into intervals using the values of x found in the previous step. We only found 1 in the previous step. I'm going to circle that number. And write the entire equation of the function in each interval, replacing the absolute value bars with parentheses. So leave a little space when you do this next part because we're going to be adding something to it that we haven't been told yet. So I'm taking all the numbers from negative infinity to infinity and I'm breaking them into two parts. All the things to the left of -2, all the things to the right. What this is telling us to do in here is take the original equation, write it down on the left side, replace the absolute value with parentheses, write it on the right side, replace the absolute value with parentheses. Step 3 is pretty important. And when you actually do these problems, you won't actually show step 3. I mean, you can, but there's really no need to. Determine the sign of each expression in the parentheses. So we're supposed to determine, is this going to be an x plus 2, or is it going to be a negative x minus 2? Is this one going to be an x plus 2, or is it going to be a negative x minus 2? Determine the sign of each expression in parentheses. I'm reading number 3 here. By choosing a value from each interval and substituting it in for x, place the sign in front of the expression on each interval. So let me explain. Got this number line up here. We're going to choose a number to the left of -2, like a -3. We're going to choose a number to the right of -2, like a 0. If we choose x equals a -3, and we plug it into x plus 2, we're going to get -3 plus 2. This is a -1. If we plug in a 0 into the x plus 2, it's going to be 0 plus 2, which is going to be a 2. We're not concerned about the numbers we're getting. We're concerned about, is it going to be negative or is it going to be positive? A -1's negative, a positive 2 is positive. Let me show you this big picture, what we just did. Because once again, step 3, you're not going to actually show when you do your work. I'm just trying to explain it to you. Let's review what's happened so we can check this out because this is probably sounding overwhelming. Step 1, take what's in the absolute value, set it equal to 0 and solve it. If you have multiple absolute values, you're going to do this multiple times. Take each of these solutions, put them on a number line, and circle the number. Then pick a test number in each interval. To the left of -2, I chose -3. You plug it in here mentally. -3 plus 2, is that positive or negative? That's negative. Pick the 0, put it in here for the x plus 2. 0 plus 2 is positive. This is going to be positive. That's the work that we just showed down here. If you get a negative answer, we're going to put a negative on the outside of the absolute value. If you get a positive for the answer, we're going to put a positive on the outside of the absolute value. We then simplify this. So if this is a negative, you could even put the negative in front of the 2 if you wanted. If you distribute the negative, it's going to be a negative x minus 2. If you distribute the 2, you're going to get a negative 2x minus 2. Combine that with this. You know what? I multiplied wrong. I'm trying to do too much at once. If I distribute the 2, I'm going to get 2x plus 4. Agreed? If I distribute the minus, it's going to change the signs. You get negative 2x minus 4. Bring down the minus 3. Combine like terms, so we get negative 2x minus 7. Does that look familiar? It should. Same thing we had up here. This is an analytical way of doing it. This one here, if I distribute the 2's, I'm going to get 2x plus 4. If I distribute the pluses, I'm still going to get 2x plus 4. Combine the 4 and the 3, you get a plus 1. Does that look familiar? It should. Same thing we had up yonder. Step 4, simplify the expressions on each side of the intervals. We did that up there. Distributing the signs and determining the steps and combining them like terms. We did that up here. A lot of things are happening in line 2, even though that's actually steps 2, 3, and 4. Then write your piecewise function. F of x equals, we got one piece, negative 2x minus 7. We have another piece, 2x plus 1. How do you determine the domain restrictions? Well, this negative 2x minus 7 came from numbers to the left of negative 2. X is less than negative 2. These on the right came from numbers that were bigger than 0. I'm sorry, that's not true. They came from numbers that were to the right of negative 2. That's what I wanted to say. So x is greater than negative 2. There's no hole in this graph. This negative 2 is inclusive. We circled it. That's what that means. So we need to put an underline under one of these so that it includes it. Doesn't matter which one because they're coming to the same spot. That is an analytical way of doing this. It's one example. I'm going to show you a couple more, and hopefully you're going to get more comfortable as I show you more examples. Compare your piecewise defined function, what you wrote in step number 4, to the above equation that you wrote at the beginning. Are they the same? Should they be the same? Explain. So look at them. They are the same. We're supposed to, well, let's first say that. They shouldn't start out with they. The equation from step 4 is the same. You know what? I don't want to say equation. I'm sorry. So let's compare the piecewise defined functions. The piecewise, I'm really sorry that you have to erase that, function in step 4 is the same as the one we wrote at the beginning. Are they the same? We answered that. Should they be the same? Yeah, they should be the same. Yes. We can say they now because they is referring to the functions we mentioned. They should be the same. Why should they be the same? Well, because both equations represent the same absolute value function f of x. I mean, it's kind of a silly question, but we're answering it. Because both equations represent the same absolute value function f of x. Dunsies. Let's do another. Now I have another video posted on my website that explains how to do this problem without doing any steps 1 through 4. It's just going right to the graph. I like that better than what I'm going to show you here. But what I'm showing you here works all the time, and just straight up graphing it technically works all the time, but sometimes it's harder. So we want a plan to be able to do this no matter what the function is. So what we're supposed to do first, take each of these things in absolute values, set them equal to 0, and solve them. So our domain is going to be broken apart. And I did a terrible job of writing this. This is a negative 4, not a positive 4. Our domain is going to be broken apart at negative 4 and 1. Therefore, we're going to draw a number line. And from left to right, negative 4 comes first, 1 comes second. So write those in and circle them, please. Then pick a test number To the left of -4 on a number line, choose anything you want. I'm going to choose -10. Pick something between -4 and 1. I'm going to choose 0. Something to the right of 1, I'm going to choose +10. Doesn't matter what you choose, folks. I'm going to make sure this stuff doesn't bleed together. That's step 2. Also part of step 2 is we're going to write the original function g of x. We're going to replace the absolute value bars with parentheses. We're going to do that in each of these intervals. It would have been quicker if I had just written it at this point instead of copying and pasting, but what are you going to do? All right. Step 3, so step 2 is draw the number line, put the numbers on that you found solutions to from step 1. Throw some test points in there, 1 from each interval. Rewrite the equation 1 time per interval, replacing the absolute value bars with parentheses. Step 3, which is hard to show the work for this, but also not that important to show the work for this. We're going to take in each interval, right now we're on this side here, we're going to take the -10 and we're going to mentally take this -10 and we're going to plug it in to this. Is a -10 plus 4 positive or negative? I heard negative, so we're going to put a negative on the outside. Then we're going to take this -10 and put it in here. -10 minus 1, is that positive or negative? It's negative. We're going to put a negative on the outside. We're going to do the same thing in this next interval. We're going to take this 10, this 0 I should say, and plug it in. 0 plus 4 is positive, put a little plus sign. 0 minus 1 is negative, put a little negative sign. Then we're going to plug 10 in. 10 plus 4 is positive. 10 minus 1 is also positive. What happens next is you remove the parentheses by distributing the minuses or pluses. So in this first one, we're going to have -x minus 4 minus x plus 1. Combine like terms, you get -2x minus 3. What's that mean? Anytime x is less than -4, your equation is going to be y equals -2x minus 3. This next one, if you put 0 in, which I guess we already did that, distribute the 0, scratch that, distribute the plus sign, is what I meant to say. We're going to get x plus 4. Distribute this minus sign, we're going to get minus x plus 1. Combine like terms, your x's cancel, and you get y equals 5. Between these x values, -4 and 1, we're supposed to be graphing y equals 5. That's what that means. Over here on the right, distribute the plus sign, you get x plus 4. Distribute the plus sign, you get plus x minus 1. Combine like terms, you get 2x plus 3. Step 4, which we've already done, simplify the expressions with the interval by distributing the signs and then combining like terms. We did all that. Write the equation as a piecewise function. So we have 3 intervals, so we have 3 parts. This was function g. The left part is -2x minus 3. When is this happening? Whenever x is less than -4. The middle part, g of x is equal to 5. When is this happening? When x is between -4 and 1. The last part is 2x plus 3. When is that happening? Whenever x is greater than 1. Now we're not quite finished. It would be easy to mess this next part up. This is implying, the way I have this written, that there's going to be a hole in the graph someplace, because we don't know what to do when x is -4 or when it's 1. Each of these pieces come together. In other words, this is a continuous graph. So to make this continuous, I am going to include the -4 and the 1. Well, I could include them like I just did, Or I could have put this down here. Makes no difference because they're coming together in the same spot. Or I could put the equal sign for the -4 in either of these. It makes no difference. I typically put mine in the middle. So that's a complete-ish problem. We answered what we were supposed to do. Now graph the function on the grid below. Let's write that down. Graph it. Check your graph in your graphing calculator. Identify the domain and range of the function. So this graph is broken apart at -4 and at 1. I'm going to draw these dashed lines here. They are not necessary. This can be used as a guideline. These are not vertical asymptotes. It's just a guideline. To the left of -4, we're supposed to graph the function -2x minus 3. So to graph that, I know the slope's -2 and the y-intercept's -3. I can't see where that is. What I could do is figure out where this hits -4. If I put a -4 into this, -2 minus 4, -2 times the -4 is 8. 8 minus 3 is 5. So that tells me when x is -4, y is 5. That's the boundary of this graph. From there, the slope's -2. So I go up and to the left 2. Why am I going up and to the left instead of down and to the right? Because this gets graphed on this part of the coordinate plane when it's less than -4. I put a closed dot there. That is true. It should be an open dot from what I wrote, but the next part of this graph is going to connect at that same spot. So the closed circle is going to close that in. From -4 to 1, we're supposed to graph y equals 5, which is just a horizontal line, like so. The last part, 2x plus 3. I can do this in a couple ways. I can figure out where this is hitting 1 by putting 1 in. 2 times 1 is 2. 2 plus 3 is 5. That confirms this dot that I already have here. Slope from that's 2. So if I go up 2 and to the right 1, it's going to give me this. You could also see if I extended that down with the same slope, it's going to cross the y-axis at 3, which the y-intercept was 3. So we graphed it. I have to identify the domain and range. This graph goes left and right forever, and it's continuous, so it's -infinity to infinity. The range, it goes as low as 5, it includes 5, and it goes up forever. So there is the domain and range. So a couple more examples. This next one, we're going to do all the stuff that we're supposed to do without it telling us how to do it. So I'm going to draw a number line. I'm going to show you the necessary things that you need to write if you're going to use this method of doing it. Then take this absolute value and think to yourself, what number could I put in for x to make that equal to 0? It would be -2. So x plus 2 equals 0. You solve it, you get -2. So we're going to put -2 on our number line, circle it because we include that number. If you set 2x minus 3 equal to 0 and you solved it, you would end up with 3 over 2 is your solution. Can you show the work for that? Yes, I did it for the first 2 examples. Do you have to show your work for that? No. Just make sure that you do it correct. Just done step 1, we started step 2. This is going to break this number line into parts. I'm going to write down this function in each of these parts, and I'm going to remove the absolute value. I'm going to use parentheses. So y equals parentheses x plus 2 plus parentheses 2x minus 3. I'm going to put that in each of these parts. like so. I'm then going to pick a test number to see if each of these parentheses will be positive or negative. So if I choose something like -10, 0, and 10, doesn't matter what you choose. As long as the number here is to the left of -2, is between -2 and 3/2, and to the right of 3/2, doesn't matter what you pick. If I put a -10 into this first set of parentheses, it's going to end up being negative because a -10 plus 2 is -8. If I put a -10 to the next one, that's going to be a -20 minus 3. They're both going to be negative. So to get rid of my parentheses, we're going to get -x minus 2 minus 2x plus 3. This simplifies to y equals -3x plus 1. If I put a 0 in for these to figure out what sign is going to be, 0 plus 2 is positive. 2 times 0 is 0 minus 3 is negative. Distribute the pluses and the minuses. Combine like terms. We get y equals -x plus 5. For this last interval, if I put a 10 in, I'm going to get a positive. If I put a 10 in the next one, it's also going to be positive. So y equals x plus 2 plus 2x minus 3. Combine like terms. We get y equals 3x minus 1. The directions were to rewrite this as a piecewise function, then to graph it. So my piecewise function, this was function f, has 3 pieces. -3x plus 1, -x plus 5, and a 3x minus 1. -3x plus 1 is to the left of -2. The middle part is between -2 and 3/2, and the right part is greater than 3/2. I circled these numbers because they're inclusive. I can include those numbers in any of these intervals that I want, any of the ones that have the boundaries, so I typically just put it in the middle. We finished the rewrite part, now we're supposed to graph it. To help with this, I'm going to lightly draw a vertical dashed line at -2 and 1.5. That's what 3/2 is. To graph this first part, I'm going to first figure out where this hits the boundary. I'm going to put a -2 into this. That's the boundary of this. -2 times -3 is +6, plus 1 is 7. So at -2, 7, there's a dot. And I'm supposed to graph this. On the left of this, the slope's -3. So I go down 3 into the right one, which is the wrong direction because I want to be on the left part of the graph. I'm going to go up 3 into the left one. It's going to put me like so. The middle part of this is the line -x plus 5. What's nice about that one is we can see where the y-intercept is of that, so it's included in our domain. And the slope's, the slope's -1. So that's going to look a little something like this. This needs to be a little bit longer here. Goes until it hits that dashed line. Like so. Then the last part, -3x minus 1. We already see where it's connected. It's connected at that point we had graph. So from there I go up 3, 1, 2, 3 into the right one, up 3, 1, 2, 3 into the right one, up 3, 1, 2, 3 into the right one. Connect those little fellas with your nice ID card. Something like that. 1, 2, 3. Just recounting. So there's your function graphed. I meant to make that last part green. So there we go. We got that little fella graphed. We have the equation written, so it's finished. This last one is a little different. It says perform the described process for this function. It doesn't say to graph it, and that's great because we don't know how to graph this, quite frankly. This one is different because it's a rational function. It's rational because you're dividing by a variable. This is going to have some type of discontinuity as a result of that. But the process we've been using was going to work for this, and let's use that process. Let's draw a number line. On this number line, what would I put in here for the 5 minus x? What would I put in for x to make that equal to 0? I would have a 5. Put that over here on the right. It includes that. What would make this domain equal to 0? The negative 3. I put that on the left. I'm going to circle it and put a line through it. So I'm going to write down the work that just happened there. Here's the work. For the absolute values, you take what's inside, set it equal to 0, and that's where this 5 comes from. You also need to account for restricted numbers, numbers that you can't use. The denominator can't be equal to 0, so x plus 3 can't be 0. Therefore, x can't be negative 3. That needs included on the number line. This is the part that makes this problem different than the previous examples, restrictions. We are then going to write in each of these y equals, in parentheses, 5 minus x minus 8 over x plus 3. In other words, we're going to write in each interval the original function, removing the absolute value bars and putting in parentheses. We do that 3 times because we have 3 intervals. We have 3 intervals because we had 2 numbers that either made the absolute value 0 or made this whole thing undefined. Pick a test number in each interval. It's not always, you don't always have to use negative 10 and 10. It just seems like that's worked out well for me so far. And plug them in to the parentheses to see if you get positive or negative. If I put a negative 10 into this, 5 minus a negative 10 is like 5 plus 10. It's going to make that positive. If I put a 0 in for this, 5 minus 0 is positive. Put a 10 into this, 5 minus 10 is negative. Simplify each of these little fellas by distributing the plus or minus that we determined. Now, I don't know if you just noticed what's happening here on the left, but this simplifies to this, but you could factor a negative 1 out of this. If you did, guess what happens? The x plus 3's cancel because you're multiplying and dividing by an x plus 3. So this just becomes negative 1. That's pretty cool. Notice how this is identical to this. They're both plus. So that means this also simplifies to negative 1. Over here on the right, if you distribute the minus, we're going to get something different. Negative 5x plus x minus x over x plus 3. If we combine like terms, we're going to get x minus 13 over x plus 3. So now we just need to write down our function interval notation. So we have p of x equals. Please keep in mind, we got the same answer for each of these. And this interval is everything to the left of 5, but not including negative 3. So to write that, perhaps not the easiest thing in the world, we would simply say x is less than 5 Let's go less than or equal to. These two graphs come together at 5. But x can't be negative 3. And then the other part is x minus 13 over x plus 3, and that's when x is greater than 5. Once again, this underlining equal could go in either of these spots. I just wrote it in the first one for no particular reason. So this is the answer to this problem. Last question, what must be taken into consideration for the function p of x that did not have to be considered before? We've mentioned it, we should write it down. Since p of x is rational, then the restricted values must be excluded from the constraints of the piecewise function. To be clear, that's why we did the things that are highlighted in green. We said denominator can't be equal to 0. We put that answer on this number line. We said we put a not equals over top of it by putting that little slash through it. And that made this happen over here on the right. X can't be negative 3. That concludes these notes. There's a lot of information, and well, really it's a little bit of information, but it's a tough process that just needs practice.